So we're going to keep in the spirit of some basic proofs, and I want to focus on one big proof, and then if it doesn't go on too long, then I'll do another little quick proof. But the big proof is this statement that the square root of 2 is irrational. Now you can find proofs of this all over the place. All the ones that I've seen have essentially boiled down to the same idea, but there are plenty of proofs that the square root of 2 is irrational. The big feature of this one is we're gonna prove this by way of contradiction. So remember, we like to start PF, and we're going to say we will proceed by way of contradiction. And you're going to see me say BWOC a lot. So proceeding by way of contradiction. Suppose, this is the correct way to spell the word suppose, square root of 2 is rational. Well, by our definition of rational, that would imply that there exist integers p and q such that square root of 2 equals p over q in lowest terms with q not equal to 0. And I'm just going to warn you, this lowest terms things is going to be sort of the key. All right, so let's start with square root of 2 equals p over q. And let's multiply both sides by q. So I get square root of 2 times q equals p. Then let's square both sides. So now I get 2q squared equals p squared. But recall, p is an integer, and p squared is even. That implies that p is even. And why is that? Why do we know that? Well, if we think back to what we did last time, when we did our proof by contrapositive, we proved exactly that if n squared is even and n is an integer, then n is even. Well, guess what? I can restate this by saying if p squared is even and p is an integer, then p is even. Okay, so we proved this last time. Sometimes when we reuse something, we say this is true by the lemma we proved previously, or by something that we've proved previously. So just as a heads up, if I ask you to prove this in like a quiz or an exam, I will probably state this lemma for you and then say use the lemma. Sorry, a lemma is like a theorem, but just sort of smaller. So I'll either state the lemma and say prove that root 2 is irrational using the lemma, or I might just have you prove that lemma, which was this statement that we proved last time. Okay, so p is an integer and p squared is even implies that p is even by that lemma, which implies that there exists an integer k such that p equals 2k. So now we're already considering this quantity p squared. So let's throw 2k in there. So we've got 2q squared equals 2k quantity squared. We just simplify, we get 2q squared equals 4k squared. That's fine. We can divide both sides by 2. We're going to get 2k squared on the right hand side and q squared on the left hand side. But this means that I'm writing q squared as 2 times an integer, which implies that q squared is even, but we also know that q is an integer. Which means, again by the lemma, q is even. But that means that there exists an integer L such that q equals 2L. But hold on, that means p over q is 2k over 2L. Zoom in here for a sec, or not, I guess my iPad doesn't want to zoom. This is not in lowest terms. And we assumed that it would be in lowest terms, right? If I can cancel something off the top and the bottom, that means it's not in lowest terms. And so that means there's a contradiction. And when I see a contradiction, I make this little symbol. And then I color in my box. Okay, that little symbol, it just means contradiction. There are other symbols for contradiction. Let's write some other symbols for contradiction. Sometimes you just see a big X. Sometimes you see a cross-hatched X. Sometimes you see crossed swords. These all mean contradiction. All of these mean this word here, contradiction. I like that one for contradiction. All right, so that was a little fast, so I want to go back over the main points. First, let's recall this thing here. So this is a statement we proved, and it's a statement that's going to help us. So the German word for lemma is literally helping statement, or Hilfssatz. Okay, so we're going to use this statement, and the way it works is we assume, we want to prove that square root of 2 is irrational, so we assume the opposite, and then we derive a logical contradiction. So we assume that it's rational by way of contradiction. BWOC, suppose the square root of 2 is rational. Well, then we just write down the definition for rational. Then there exist integers p and q such that root 2 equals p over q in lowest terms with q non-zero. We write root 2 equals p over q, multiply both sides by q, square both sides, and we get 2q squared equals p squared. But this means p squared is 2 times an integer, so it's even. Recall p was an integer, so we've got p as an integer and p squared is even, therefore p is even by the lemma. This is the lemma. Okay, fine. So if p is even, that means there exists an integer k such that p equals 2k. Fine. Now when we plug our value in for p here, we get 2q squared equals 2k quantity squared. Simplify. 2q squared equals 4k squared. Divide both sides by 2. And we get q squared equals, guess what? 2 times k squared, which is 2 times an integer. That means q squared is even. But recall q is also an integer. So we can apply the lemma, this lemma, q squared is even and q is an integer implies q is even. Great. No big deal. So if q is even, that means that there exists an integer L such that q equals 2L. But hold on, we said square root of 2 is equal to p over q in lowest terms. But we just showed that p over q is not written in lowest terms because we can cancel a 2 from top and bottom. And that is a contradiction. Okay, so that was the main thing that I wanted to talk about in this video. Thanks so much.